Alright, so let's start. Alright, so half-wave rectifier, alright? So, this is the basic circuit of a rectifier. Half-wave rectifier. It consists of a source. Sorry, this is wrong. By mistake. It should be an AC source. Okay? It should be an AC source. Alright? So, an AC source, you know, by waveform, you see the waveform for the AC source. This is the input. Okay? And this is a simple representation of a half-wave rectifier circuit consisting of one diode only. There are some circuit also which is also half-wave depending on the connection. All right. So I mean in full wave there are two ways you can connect. You can use 4 diodes. You can use 2 diodes in a depending on the transformer and so on and so forth. But we will discuss. I think the next lab will be full wave. Okay, you'll find there are some variations of the circuit when it comes to full wave. But in half wave, sure, one diode. They are using one diode only. Because he is only rectifying the other side. Because in the cycle, we have the positive cycle and the negative cycle. He is only allowing one cycle only, or half of the cycle. That's why it's called half wave. Half of it is being allowed from the input going to the output. Alright? Like for example here, okay? For example, the current goes through that position. Alright? Now, what is now, so based on the input, which is the AC waveform, okay? The question is, what will be the output waveform? So, okay? So, in your experiment, what we will do is to measure also the input waveform and also measure the output waveform using our oscilloscope. And we should see these two waveforms coming from your oscilloscope when we try to measure it. Okay? So, but how? How it goes? How it operates? Okay. So, again, as I mentioned, a sine wave consists of a positive cycle and a negative cycle. And again, repeating, right? Repeating. Positive, negative, right? So again, so now, how it works? During the positive, for example, we all start with positive, right? During the positive cycle, since we know here, this is the positive or what we call the anode, this is the cathode, this is the positive material or the positive polarity of the diode. Okay, what it will do during the positive cycle? What do you think? It will allow to enter or not? It will allow, right? Because since it's positive cycle and this is positive in relation to positive, now the positive will pass through. Okay, so if it's passed through, it will go to the output terminal, all right, or the output side of the circuit. So meaning, during the positive cycle, what do you expect in the output? It will create what? An output. It will allow. It will allow an output waveform. So he will allow this waveform to enter the output or to go to the output. All right. But during the next cycle, which is the negative cycle, half cycle, what will happen? This will now, so meaning during positive cycle it will turn on like a switch, allow, alright? But during the negative cycle, since this will be negative now and this will be positive, what will happen here? Stop or turn off. Huh? It will turn off, alright? Therefore, if this is off, this is open, no short circuit or no connection, what happens here? Is there an output or no? No output. So therefore, the output waveform is simply what? Zero. You will not get any output on the next cycle. So negative cycle will not be allowed going to the output. So will give you 0. Okay? And again, it will repeat. On the next cycle, second cycle, or third cycle, Again, it will what? It will allow. And then, again, not allowed. Okay? That's why this will be the expected, okay? This will be the expected output waveform of the half wave. It will allow half of the waveform only of the input. Okay? Alright? And now, and also I think, in the table, you will try to measure or you will try to calculate the voltage output equivalent of this waveform. For example, this one. Okay? You will try to see what value will be the peak-to-peak value. Take note, ha? In the table, you will be asked to. So there's a mistake in the table. Step number 4. I think step number 4.
You can see.
Step number 4. Draw the waveform of B out. It's not B out. It's B in. Draw the input. Draw the what? The waveform. Step 4. Draw the waveform of the of B out. It's not B out. It's B in, because we are talking of B in. This step should be about B in. So scratch it. Okay, there's a mistake on the. So draw the waveform of the B in. Okay, not B out. So change it. Change it. Okay. So draw the waveform of the B in. Okay. So therefore, obviously, the waveform of the B in is this one. When you draw it, that's step number 4. Okay. That's step number 4. This is the waveform that you need to draw. All right. So this is the input waveform. It's an AC waveform. Now, it's the waveform is all about voltage and all about frequency or time. So lala,
Yes.
right? A waveform is all about voltage and frequency. So how will you get the voltage? How will you calculate, or how will you get the voltage? Okay. So we know that in a waveform, okay, based on the table, you will be asked to get the voltage. What's the second row? So you will ask to get here the V in peak to peak. Okay? So here, he will ask about the V in peak to peak. Which is obviously this one. So peak to peak means this point until this point, right? Not this point and this point, because this point is what we call peak only. Peak only. Okay? Another peak here also will be minus B peak. Okay? Plus B peak and minus B peak. And from that point until this point is what we call B in peak to peak. That is the one that we need in the. Okay, you have to calculate. You need to calculate. I will teach you how to get the value based on the waveform on the oscilloscope. It will be per division. You will find there Y divisions in the written table. You will find the table. You find that V in Y voltage per division. Wala V for division. Okay. Also same thing. With the time. Okay, the time. So which is the time? So the time is where? This is the time. In the time, we are always considering one cycle only, not the whole cycle. Okay, only one cycle. Alright, remember that. When you are considering the time or frequency of the waveform, you are considering only the whole cycle only, not the double cycle or something like that. Okay. So here, how will you measure also the time? So again, from this point until this point would be the time spent by the waveform to travel. Okay? So this one again, on the oscilloscope, you will find here per division. So, based on the range of the oscilloscope and the division, you will find the total time. How much time does this waveform travel from this point until that point? For example, here, the time given 10, the time is spent from this point to he was spending 10 milliseconds to travel. Okay? So the last table there, you will find there a question which is the frequency, right? And from this given time, you can calculate the frequency. Alright? That is what's the formula? 1 over time. So this will give you 1 over, this is an example, 1 over 10. So frequency here is about, how much? 50? 1 over 10 milli. Please, can you check? I think it's 50. It's 50 hertz or something. 1 over 10 milli. 1 over 10 milli. Okay, 100 hertz. Okay, sorry. It's 100 hertz. So this will be equivalent to.
And if we have a frequency, we can find the time.
Huh?
And if we have a
Frequency, you can have the time, yes. But the problem, our oscilloscope will give you only the time, not the frequency. Okay? Our oscilloscope will give you the time only. Okay? The time travel. Equivalent time. There's no frequency there. So you have to calculate for the frequency based on the time. Got the idea? Alright? So, also, there's another thing. Alright? In your first table, using DMM in AC mode. So here you are asked to measure the input voltage using a DMM. Saulala? Okay. We know, take note, we know that a DMM always measure in RMS. Remember that, in RM, you know that?
Yes, sir.
In RMS value, right? In VRMS value. Alright? Therefore, the one that you will find here later, it will be different, will be a different number compared to the VRMS value. You get the idea? Alright? So here, you need to verify if your measurement or waveform is correct, try to apply the rule. Okay? Later, you apply the rule. Alright? You apply the rule BRMS because we will measure the BPP in relation to BIPP. The formula will be 2 square root of 2 multiplied by voltage peak to peak. Okay? Or that will be equal to 0.3, I think 303. Can you calculate this one? 1 over 2, 2. What's the value of this? 0.303 or 0.305, something like that.
We can use the 0.
That's BP. That's BP. Huh? 0.35. 35, not 35? B. So he was talking about 707. This 707 is this one, brother. It's not peak to peak, it's B peak only. Yes, this square root of 2 B peak, that is 0.707 B peak. This one is what you're talking about, right? Huh? You will apply that 0.7, this concept 707 is applied to BP. But for peak to peak, this is the constant value, 0.35. Yeah, there. I prepare this one because why? We are measuring B peak to peak, right? We are asked to get peak to peak values already, sir. So I don't need this one. I need this formula because I already did the peak to peak in the table. So Lala, you get the point? So I don't want this one because I was after this peak to peak. We measured it by peak to peak. So I will apply the RMS. So this RMS now, this number now should be the one coming out of the deep B in by DMM. Okay? So when you measure the peak to peak, try to calculate it. That number should be closer to the number that you measured here. It should be. If it's very far, meaning you have a mistake in your connection. You have a mistake in your measurements. But if it's closer, meaning you're in good steps. Have an idea? Okay? Now I will show you, a short demonstration how to connect it, and later on do it by your own. Is that okay?
Okay.
Alright.